All right, we begin chapter 9 with splitting. So we are going to talk about polynomial splitting at first, and then we're going to lead into splitting fields and so on. So the definition that we're going to start with here is suppose K is a subfield of C. Then L, and L is an extension of K. And F is a non-zero polynomial over K. Then we say that F splits over L if it can be written as a product of linear factors. So that, of course, there's some limiting coefficient, and then we have some linear polynomials where each of the a's are in L, okay, and the k is in K. All right, so we say it splits over an extension or a field containing L if it splits into a product of linear factors. Okay, so it breaks down as far as it can break down over L if we use those coefficients. So we know that, as an example, if K is equal to Q and L is equal to C, then every non-constant polynomial. I think I was supposed to say non-constant up here. Non-constant. Just because this definition doesn't really make sense with constant polynomials. Anyways, then every non-constant polynomial splits over L. By the fundamental theorem of algebra, which I'm just going to abbreviate as FTOA. Okay, so the fundamental theorem of algebra says, hey, it doesn't, and in fact, it doesn't even matter. You don't even need K to be Q. So K could have been any subfield of C. If you use L as all of C, the fundamental theorem of algebra tells us, well, everything splits over C. So C you can use to split any polynomial. Now the question is, well, do we need all of C, right? So do we need all of C? And the answer is in general, no. We really just need to add in sort of the finitely many roots. So as a follow-up example, let's look at the polynomial t cubed minus 2 over q. And let's set L to be q adjoin the real cube root of 2 and then omega, where omega is e to the 2 pi I over 3. Okay, so this is a field that we've seen over and over again. We're going to continue to see it. Then over L, f can be written as t minus the cube root of 2, t minus omega cube root of 2, t minus omega squared cube root of 2. All of those elements, all those coefficients, these numbers are certainly in L. And so f splits over this field. In fact, more is true. All, or what do I want to say here? L is the smallest field over which f splits. So all we did is we took Q, the base field, and we added just enough numbers, just enough complex numbers to get access to the roots. And we didn't add more. Like we didn't add like a square root of 5 here or anything like that, any extra stuff. This was the minimal amount that we needed to add to get access to all the roots. Okay. Let's see, another example that we've seen is the polynomial, let's see, t squared plus 1 times t squared minus 5. This previous polynomial was irreducible, but when you're looking at splitting, it doesn't matter if the polynomial is irreducible or not. It can be reducible, as in this case. And we're going to look at this over Q. Then f actually splits over Q adjoin I, comma, root 5. Why is that? Well, f of t, if we have access to I and root 5, we get t plus I, t minus I, t plus root 5, t minus root 5. Furthermore, this L is the smallest field over which f splits. There is no smaller field that contains sort of all the roots of f. This is the minimum amount that we need to add. Okay, so we say that a polynomial splits over some extension if we can write it as a linear factor, and we're going to see pretty soon that there's always actually a smallest extension over which you can split your polynomial, and we'll end up calling that the splitting field in a minute.